Steam locomotives once devoured forests and mountains of coal just to move a single train. Yet by 1900, over 90% of global rail traffic was powered by coal alone, and efficiency barely scraped 8%. This is how the evolution of fuel power turned industrial dreams into dependence, crisis, and invention. What forced a total rethink of the fuels that built modern transport? And which breakthroughs truly changed the tracks? In 1804, Richard Trevithick's Penny Darran locomotive rumbled across a Welsh tramway, powered by coal and steam. The machine's iron wheels and compact boiler signaled a new direction for rail travel. Coal, with its energy density of about 24 megajoules per kilogram, delivered nearly twice the punch of wood. This allowed Trevithick's engine to haul heavier loads and run longer distances than anything fueled by timber. Yet early steam engines were far from efficient. Only about 6 to 8% of the coal's energy reached the wheels, the rest lost as heat and exhaust. When George Stephenson launched the Stockton and Darlington Railway in 1825, his choice of coal was deliberate and calculated. The railway's ledgers show coal was not only abundant in Northumberland, but also stable in price. Stephenson's contracts with local collieries guaranteed a steady supply, while his recorded remarks predicted unrivaled economy for the new line. On opening day, crowds of pitmen and labourers lined the tracks, their faces streaked with coal dust as locomotion number 1 steamed past. The spectacle underscored coal's growing dominance, not just as fuel, but as the backbone of an industrial network. The technical ceiling remained stubbornly low. Even as more lines adopted steam, only a fraction of each shovelful of coal actually moved the train. Still, the logic was irresistible. Coal's higher energy density meant fewer stops, longer routes, and a supply chain that could scale with the ambitions of a growing nation. The decision to standardize on coal set the foundation for a railway system that would soon span continents. But it also locked the industry into a fuel whose limits were already visible in the haze above the tracks. By the late 19th century, coal had become the lifeblood of global railways. More than 90% of trains worldwide ran on coal, and the infrastructure to keep them moving was immense. Coaling depots, water towers, and sprawling maintenance yards lined the tracks from Manchester to Milwaukee. Each journey demanded careful planning, not just for distance but for the next stop, to shovel in more fuel and take on water. The fireman's job was punishing, hours spent in the heat of the cab, shoveling tons of coal into the roaring firebox, eyes stinging from soot and smoke. On busy routes, crews could burn through several tons of coal on a single run, leaving a trail of black dust and cinders in their wake. The burden of coal was felt most keenly during moments of crisis. In 1902, a massive coal strike swept across the United States. With fuel supplies running low, railroads like the Southern Pacific and Santa Fe faced a stark choice: halt operations or find another way. Engineers scrambled to retrofit locomotives for heavy fuel oil, especially on the West Coast where oil was closer at hand. Company memos from that year describe the first conversions. Steel tanks welded into old coal bunkers, crude burners bolted beneath the firebox. Firemen, once chained to their shovels, now managed valves and watched blue flames flicker across the grates. The new system was less labor-intensive and cleaner in the cab, but it demanded new skills and constant attention to prevent overheating. Oil-fired steam caught on in regions where coal was scarce or expensive, though the basic inefficiencies of steam remained. The coal empire had shown its limits, and for the first time, railways looked seriously at fuels beyond the black rock that powered an era. In 1879, Werner von Siemens introduced Berlin to electric rail, running a demonstration train on 180 volts of direct current. It circled a short track at 8 miles per hour, quietly sidestepping the smoke and soot that defined coal-fired steam. The promise was clear. Electricity could move trains cleanly through crowded cities. By the early 1900s, urban planners saw electric traction as a way to make city rail safer. The urgency peaked in New York after a deadly 1902 crash in the Park Avenue Tunnel, where steam and smoke blinded engineers. In response, city leaders banned steam locomotives south of the Harlem River by 1908. The New York Central Railroad spent over $3 million wiring tracks and installing third rails, a massive investment that paid off with quieter, safer trains and cleaner air. Grand Central's electrification alone would equal more than $100 million today. The shift also meant fewer staff were needed, as electric trains ran reliably with less labor. Beyond city limits, another transformation was underway. Firms like Sulzer in Switzerland and EMD in the United States developed diesel-electric locomotives. By the 1920s, these engines burned oil to generate electricity for motors on each axle, freeing trains from overhead wires and third rails. Diesel locomotives cut maintenance costs and eliminated the need for firemen, sparking labor unrest as steam crews lost their jobs. By the 1950s and the 1960s, railroads from Santa Fe to the Soviet Union retired their last steam engines, replacing them with diesels that could run for days without refueling. The era of coal and steam gave way to a new landscape. Electricity in the city, diesel on the open line. Today's railway landscape is defined by a careful balance between electric and diesel power. About 45% of the world's trains now draw their energy from the grid, while the remaining 55% still rely on diesel. This split is not just a technical detail, it shapes how and where trains run. In Europe, 56.1% of tracks are electrified, but these lines handle more than 80% of all rail traffic, especially in dense corridors where overhead wires and substations make high-speed and frequent service possible. Diesel, on the other hand, remains the workhorse for freight and for regions where installing electric infrastructure is not practical or affordable. The United States, much of Asia, and large parts of Africa and Latin America still depend on diesel for long-haul and rural service, a reality reflected in maintenance records and locomotive orders worldwide. Yet environmental pressures and policy targets are pushing the industry to look beyond both the wire and the oil tank. In 2018, a new chapter began on the regional lines of Lower Saxony, Germany, when Alstom introduced the Coradia Eilint, the world's first commercial hydrogen-powered passenger train. Instead of burning fossil fuels or drawing directly from the grid, this train uses hydrogen fuel cells to generate electricity on board, emitting only water vapor. Service logs from its first year show that the Eilint routinely covered up to 1,000 kilometers on a single tank, matching the endurance of many diesel units. Passenger accounts described a ride that was both quiet and odorless, a stark contrast to the noise and fumes of traditional engines. Since then, hydrogen trains have expanded to other parts of Europe, offering a glimpse of what zero-emission regional rail could look like. Still, hydrogen's adoption depends on reliable supply chains and infrastructure, and for now, it remains a solution best suited for non-electrified routes where batteries or wires fall short. The arrival of hydrogen power signals real progress, but it also highlights why railways continue to experiment with multiple fuel options in the search for cleaner, more flexible traction. On the night of July 14, 2021, floodwaters swept through Germany's Ahr Valley, tearing out tracks and leaving overhead wires twisted and useless. Within months, Deutsche Bahn restored passenger service on the battered line, not with diesel, but with battery-powered trains. Stadler Flirt Akku units ran the 20-kilometer route between Remagen and Walpersheim, drawing power from onboard lithium-ion batteries charged at Remagen station. Each three-car set covered up to 80 kilometers per charge, matching the demands of the emergency timetable and running at 30-minute intervals during peak hours. With no catenary to rely on and diesel sidelined, battery trains proved their worth as a stopgap, keeping communities connected while repairs dragged on. Operators reported reliable performance and quiet operation, and regional authorities called the trial a milestone for resilience. The R-Valley response showed battery trains could fill gaps quickly, offering a practical alternative whenever wires go down. Japanese rail operators have been testing a new approach, combining hybrid train hardware with predictive energy management software. On Tokyo's Yamanote line, teams launched trials between 2019 and 2022 that put advanced algorithms in charge of acceleration, braking, and energy recovery. The trains used onboard sensors and real-time data to anticipate each stop and optimize power use, adjusting speed and coasting patterns with remarkable precision. The result was clear in the numbers. JR East's internal reports show energy savings between 5 and 10% across test segments. This software-guided hybrid system did not just trim electricity bills, it offered a practical path toward net-zero rail corridors in one of the world's busiest cities. For engineers, the project mapped out how digital control and hybrid traction could deliver measurable gains, while leaving open the question of how quickly these savings can be scaled across entire networks. Right now, over half of the world's trains still burn diesel, even as battery and hybrid locomotives gain ground. With global rail demand rising, every new fuel choice shapes how we move, breathe, and build tomorrow. The future of fuel power remains an open track, ours to decide.